Okay, so today we're going to talk about equilibrium. Okay, so we're going to talk about what it is and go over a couple things about it. And then your homework assignment is to complete this 8EQ1 here. There's 3 parts to it, so make sure you do all 3 parts. Okay, I did include the answers to it as well, so make sure you give that a shot. Okay, so let's talk about equilibrium. So, first of all, most of the reactions we've talked about so far, we've only talked about them going in one direction, right? We've only talked about them going from reactants to products, right? However, most reactions or a lot of reactions actually occur in both directions. So what we have is reactants going to products, and then some products turn back into reactants. So they're kind of like going back and forth. Okay, so some reactions don't go all the way from reactants all the way to products. Some stop at some point, and it's not necessarily that the reaction stops. It's just that the rate of the forward and the rate of the backwards reaction are equal. So the overall change is zero. The overall net change is zero, right? So if you're looking at this chart here on the side over here, we have concentration versus time. So if we have this reaction A plus B is in equilibrium with C plus D. So we don't say yields per se when we talk about equilibrium reactions. We say the reactants are in equilibrium with the products. Okay, so in this chart here, we're actually only starting with A and B. So the concentration is high for A and B, and the concentration of C and D is zero. Over time, A and B will turn into C and D. So A and B will go down, and C and D will go up. And then there comes a point when the concentration of C and D and the concentration of A and B remain constant. So you see that they're not equal. The concentration of C and D are actually greater than that of A and B. We would actually call this reaction, we would call this a product favored reaction. So this equilibrium reaction favors the products. There's going to be more products than there are reactants at equilibrium. Okay. So at equilibrium, the amount of products in the reactants, the amount of products is staying constant, the amount of reactants is staying constant. They are not necessarily equal. Okay, but what's equal at equilibrium is the rate at which products turn into reactants and reactants turn to products. Okay, we call this a state of dynamic equilibrium. Dynamic means that it's still moving. It's dynamic but equal, right? We still keep constant activity. It's dynamic, but it's balanced. So the amount of products and the amount of reactants are not changing. Okay, they're not changing. Again, this does not mean that the products and reactants are equal in concentration. It just means that they are moving backwards and forwards at the same rate. Okay. Now, for an equilibrium expression, so for a reaction here, this reaction right here, we can write an equilibrium expression. This is a constant K. It's equal to the concentration of the products to their coefficients over the reactants to their coefficients. Concentration of reactants to their coefficients. When we put something in brackets like this, we mean the concentration in molarity. So this is the molarity of C to its coefficient times the molarity of D to its coefficient over the reactants, concentration of A to its coefficient, concentration of B to its coefficient. Okay, this is called the equilibrium expression. K is known as the equilibrium constant. Okay, now this K is for each reaction is a constant at a specific temperature and pressure. Okay, so every temperature and pressure, every reaction, every equilibrium reaction has a specific K at a specific temperature and pressure. Okay, we call that the equilibrium constant. You'll see it three different ways. You see KEQ, that means the same thing as K and same thing as C. These are all the same. KEQ, K, and KC are all the same. They describe ratio of products reactants in a reaction equilibrium. Kc is typically used for aqueous or aqueous reactions and used concentration. Keq is used typically for aqueous and gaseous reactions, usually gaseous, but they can all be also used for concentration. And all of these things are pretty equal. When we write equilibrium expressions, we do not include solids or liquids. Okay, we do not include solids or liquids. We only include gases if it's a gas reaction, gaseous reaction, or we only include aqueous or AQ if it's an aqueous reaction. Okay, kind of a lot to put in. This is kind of a lot to absorb right here, believe it or not. But we'll be practicing a lot of this stuff, and hopefully we'll use this as a reminder, okay? Be writing some equilibrium expressions. Remember that solids and liquids are not written in the equilibrium expressions. Okay. Now, if we're using Kp, Kp is with pressure. So Kp is a pressure, is the equilibrium constant at a certain pressure. This is for gaseous reactions. Okay, we can use concentration for gaseous reactions as well. Okay, we can use Kc for gaseous reactions. It's fine. Okay, but we can also use Kp for gaseous reactions. Now, Kp is just the products over reactants, but it's the pressure of the products to their coefficient over the pressure of the reactants to their coefficient. Okay, and we use ATM here. We're going to be using ATM to calculate Kp. Just be careful because Kp is not equal to Kc. Kp is not equal to Kc. What Kp is actually equal to, I should have really put this in the last slide here. Maybe I'll do that really quickly. This is really, I should have put it here. Kp is equal to Kc times RT to the delta N. Now, we can actually, if you really wanted to, we could actually derive this equation because if you think about it, concentration is moles per liter, and we can relate moles to pressure using PV equals nRT, and that's basically what we're doing here. We're just changing pressure or concentration of pressure. Really what we're doing here for each one. Could derive it if you want, but it is what it is. So Kp equals Kc times RT to the delta N. Now, delta N is the change in moles of gas. Okay, so it's the number of moles of products, number of moles of gas of products minus the number of moles of gas for the reactants. Okay, I believe this is actually given to you on the reference sheet. Could be wrong. Oh, maybe I'm wrong. Yeah, you have to memorize that. Yep, you just got to know it. Sorry. So you do have to memorize this. But just remember, it's like PV equals nRT. It was RT to the delta N. ACRT at delta N. Now, some of the terms that we talk about, or the way we talk about equilibrium expressions, or the properties of K. If K is greater than 1, we say that products are favored. So any number greater than 1, we say the reaction favors the products. If A is less than 1, then we say reactants are favored. Because remember, it's products over reactants. So if there's more products than reactants, then we say it's product favored. If there's more reactants than products, then K would be less than 1, and we say reactant favored. If we reverse a reaction, so we flip it, we flip the reactants and products, we flip them, that means we just flip the K. It's the reciprocal of the K, so 1 over K. If the reaction is multiplied or divided by coefficient, the K is raised to that power. So if we multiply a reaction by 2, we take the K and we square it. Okay. If we divide a reaction by 2, then we take the square root of K. Just like we did with like Hess's law. You remember like Hess's law? Okay. But instead of multiplying the K, we're doing it to the power of. Because remember, the coefficients for K are powers. So if we change the coefficients, we change the powers. If we combine reaction, we combine the Ks. So we multiply the Ks together. And then again, that Kp equals Kc times RT to the delta N, where N is moles of gas produced minus moles of gas reacting, and R is that ideal gas constant, 0.0821. Oh, no. Let's look at one of these. So writing the so this is the work that you're going to be doing for homework, or whenever you're done, whenever I'm done talking here. You're writing Kc equilibrium expression. So for the first couple, it's just gas. That's fine. And then all those are fine. You have to balance these first, and then write the Kc expressions. Then we get down like 7 to 12 or 7 to 11. I got rid of 12. 7. These ones, you just have to be careful because some of these have solid in them. We do not include solid in the equilibrium expression. Okay, so this would be not included. So this would just be concentration of Ca2 plus and concentration SO42 minus on top. Okay, same thing here. You would not include this solid or this solid here in the equilibrium expression. Okay, you wouldn't include this liquid in the equilibrium expression. Don't include this solid in the equilibrium expression. Okay. Okay, and then 1, 2, let's see. So for like number 3 here, this one, we're taking it and we're multiplying it by 1/2. So the K, the equilibrium constant here is 155. So the K here would be 155 to the 1/2 power. This one, you're just flipping it. You're flipping the reaction. So it would be 1 over 6.81. Then when you get to 5 here, you're combining these two reactions to create this reaction. So you're manipulating them just like you do Hess's law, okay, to find the new Kc. So these two, to find the Kc for this one. Okay, so if you flip it, you put 1 over. If you have to divide it by 2, you 2 to the second power, or do it to the 1/2 power, and then you multiply the Kc's together. Okay. So that's all the properties of K, and then this one's just finding Kp using Kc. Okay. And then the last thing here is going to be something like this problem here. So here we have this reaction. It has a Kc of 4.06. If 0.1 moles of CO and 0.1 moles of H2O are placed in a 1 liter reaction vessel at this temperature, what are the concentrations of reactants and products? So basically here, we're not Tomorrow we're going to talk about rice tables, but right now we're just talking about if we start with only reactants or only products, then what's going to happen is you're going to start with so the reactants, there's 0.1 and 0.1 of each. So first you write the Kc expression. So the Kc is 4.06. That's what it tells us here. The equilibrium expression is the product CO2 to its coefficient, which is 1, times H2 to its coefficient, which is 1, over the reactants. So CO to its coefficient, which is 1, and then H2O to its coefficient, which is 1. Okay. Now, the original concentrations of CO and H2O are 0.1. So it starts out 0.1, 0.1, but then it's going to shift. It's going to shift to products, and it's going to shift a certain amount. We don't know how much, but it's going to shift X. So we're just calling that X. So 0.1 minus X, and then 0.1 minus X. Okay. And then on top is how much it shifts is going to just be X. So now we have X squared over 0.1 minus X squared. So both of these things are squared, so we can take the square root of both sides. So we take the square root of 4.06 equals X over 0.1 X. And then we're going to solve for X here. When you solve for X, you'll get these values down here. So you solve for X, X equals basically 0.0332. And then you subtract 0.1 minus 0.0332, and you get 0.0668. Okay, so that's pretty much how you're going to do the last three problems at the end there. Okay, then tomorrow we'll talk about more. This is like the easiest type of problem there is. Okay, where we can take the square root of both sides. Okay, and then tomorrow we'll talk about Q, the reaction quotient, and rice tables. So basically Q will tell you, like, if we start with a specific concentration of reactants and products, which direction will the equilibrium shift? And then we use a rice table to figure out how much it shifts. And we can figure out how much reactants we have and how much products we have in the end. Okay, but for today, it's just really keeping it really, really simple. Okay, trying to get you to see the basics of it today. Okay. And that is about all I have to say.